welcome back to Arts Learning Physics. In this video, we'll be diving deep into one specific simple machine, which is pulleys, as well as how to count ropes of pulleys and apply the concepts we learned earlier. Two pulleys, which are ideal mechanical advantage, IMA, and actual mechanical advantage, AMA, as well as efficiency, right? We'll apply these concepts to pulleys, and we'll learn how to count the ropes of pulleys. So first, you have to understand that for a pulley, right, the ideal mechanical advantage is quite simple. It's just the number of ropes there are. So if you had, for example, 4 pulleys, right, and all of them had ropes like this, they're like pulling up something big. If there's 1, 2, 3, 4, 5, 6, 7, 8 ropes, then you're pulling on it over here, down here, then that means that whatever you're pulling, right, your ideal mechanical advantage is 8, because there's 8 ropes. The number of ropes in a pulley is the ideal mechanical advantage, because if you remember, that's distance in over distance out, right? Because you have to pull in a greater distance than you put out. Distance in here would be what? You would pull in a larger amount. The distance out would just pull you up like 1 meter, right? But if the pulley pulls this entire block up 1 meter, you have to understand that that means that you actually pull 8 meters, right? Because think about it. If this entire block went up 1 meter, then all these ropes went up 1 meter, which means you pulled down 8 meters, right? Because there's 8 ropes. So it's kind of intuitive why the number of ropes in a pulley is your ideal mechanical advantage. Okay? And these are the number of rope segments pulling up on the movable block. So the reason I specified up is because, okay, you might look at this pulley here, right? And if you're pulling over here, down here, well, that's just 1, right? Because you're pulling, and then how many ropes are connected to the block? Just 1. So here, you're pulling upwards, right? Okay, so you're holding it from here. You're pulling it like this. So you have this. But many people think it's just 1 because there's only 1 rope here, right? It's actually 2 because you're holding on to 2 ropes. So let me explain that. Here, you're holding on to 1 rope and pulling on, right? And there's 1 rope holding onto the weight. This here, the problem with this is there's 2 ropes actually pulling upward on the weight, right? You have twice as much leverage. This rope is pulling upward when you pull, and this rope is also pulling upward. Here, this rope is pulling downward, and you're pulling, and the block is being pulled upward, right? But how many ropes do you have here pulling it upward? You have 2 ropes, but here you have only 1. The number of ropes pulling it up, because that's what's going to move it upwards, right? That's what's going to change the location of the block. That's going to be your answer. That's the ideal mechanical advantage. And here it's going to be twice as easier because you're going to be pulling twice as much distance. Because you have what? 2 ropes that are being pulled on upward. Okay? So if you're pulling on a rope this way, this direction, you count that as a +1, okay? If this pulley system ends with a rope that you're pulling upward, that means you're going to count it as a +1. Okay? So for example, maybe we see more problems with this in action. But imagine there's another pulley here, okay, attached here. Then what would your ideal mechanical advantage be? 1, 2, 3. And then you'd count this one because you're pulling on it upward. Here you're pulling on it downward, which is the opposite direction of the weight. Okay, so yeah, pretty intuitive. These are called movable pulleys because the pulleys also move, right? When you're pulling it upward, the pulleys are moving upward with it. But here the pulleys are fixed, you see? But if the block must move up, that means the pulley must move up when you're pulling it up, right? With your ideal mechanical advantage of 2. And here, let's see. So here we have 1, 2, 3, 4, but this rope we're pulling downward, right? These ropes are all pulling upward, but my rope is pulling downward, so we won't count this rope. It's only the ropes pulling upward. So 1, 2, 3, 4. 4 is my ideal mechanical advantage. So let's walk through one example. We have 4 strands, okay? And we have a load of 800 newtons. So you know that's the weight, right? Because mass would not be in newtons. I explained that before. So we want your ideal mechanical advantage, okay? We want that first. And then we want your effort, which is your force in, right? And then we want the rope raised. How much was the rope raised, okay? So basically, distance in. How much rope did you pull on? Alright, so let's see. Ideal mechanical advantage here. 1, 2, 3, 4. This rope I'm pulling downward. These ropes are pushing upward, right? This one is I'm pulling downward to move these upward. So this one I won't count. My ideal mechanical advantage is 4. Alright? So then, if I want my ideal effort, I can do this, okay? Regularly, I wouldn't be able to find my regular effort from this. That I would have to use AMA for. But here, because I'm looking for my ideal effort, not my actual effort, I can use this. I can just say, so force in has to be what? It has to be lesser than force out, right? So force out over force in. Because your force out is larger. You're trading distance for force. So force in times distance in is equal to force out times distance out. And then if you remember, you can divide both sides by distance out. Distance in over distance out times force in is equal to force out. This is just your ideal mechanical advantage. So force in times IMA is equal to force out. And IMA is equal to force out over force in. And another way you can just think about it is whichever one has to be larger, right? Because your IMA has to be greater than 1. So force out is the larger number. That's why it goes on the top. Distance in here is a larger number because you're putting in a larger distance for a lesser force. Okay? So I can just use that. How much is my force lessened by? It's lessened by 4, right? So 4 is my ideal mechanical advantage is equal to force out, which do I know? Yeah, 800 newtons, right? The block is being pulled up 800 newtons. Over my force, which is H. 4H is equal to 800 newtons. H is just 200 newtons. So I'm trading in 600 newtons of force, but for 4 times the distance. Okay? So it doesn't take me as much effort, but I have to pull longer and farther. And then, what's the rope that it takes to raise the load? 2 meters. So if the load is raised 2 meters, then that means all these ropes have been pulled on 2 meters, right? Which means you must pull 8 meters because there's 4 ropes that you've pulled on to increase it 2 meters. Now let's try one with efficiency, okay? You have a movable pulley here, which means you're up here, right? So you're pulling up, so we'd count both of these as IMA equal to. And efficiency is 0.85 or 85%. For effort is 4 newtons. So force in is 4 newtons. So first, we can find our actual mechanical advantage, okay? So how can we do that? We can do efficiency is equal to how much I actually have over how much I'm supposed to have. How efficient is it? So AMA over ideal we know, right? 2, because there's 2 ropes that I'm pulling upward on. Is equal to 0.85. Or 0.85 times 2. AMA is equal to, so let me see what that is. That's about 1.7. Okay, 1.7. And then what? So we have that. Now we need to know the load force, okay? So force out, basically. How much is this load? How much am I pulling upward? So my actual mechanical advantage is my force out or my force in. So it should be 1.7 is equal to force in is, do I know my force in? Well, doesn't seem like I do, right? Force in, yeah, effort 4 newtons, right? Force in here. Force 4 newtons. Force out. So force out is equal to 4 newtons times 1.7. Or 6.8 newtons. If I want to find the mass of this block, then, you know, this is mg, right? The force of mg on this block. So force of gravity is equal to mg. 6.8 newtons is equal to m times 9.8. M is equal to 9.8 divided by 6.8, which should be about 1. Oh, whoops, almost screwed up there, right? I'm going to put the 6 on the top. I was wondering why I got my answer looking a bit fishy. 6.8 divided by 9.8. So yeah, always make sure you look at your numbers during pulleys. You could all easily trip up like how I almost did. Alright, that should give you about 0.69 kgs. Now let's try a large pulley system, okay? We want the effort and the IMA as well as the work done by gravity. So 94.6 kgs is our mass. We have 4 fixed plus 4 movable pulleys. Okay? 4 fixed plus 4. So we have pulleys here on each bottom side, which we're going to be pulling on the opposite direction on, okay? So if one is going up, the other pulley is going to be going down, but it still makes sense, right? These pulleys are going to go upward. They're moving upward. And these pulleys are going to stay fixed, but they're still counted as what? Still counted as ropes, right? Even movable pulleys are still counted. But here, my last one is going downward, so I wouldn't count it. It's not movable here. My last rope is just, I'm pulling downward, right? While all of these are going upward. So 1, 2, 3, 4, 5, 6, 7, 8. My IMA would be 8, because that's the number of ropes. My AMA, so my AMA efficiency is equal to AMA over IMA, right? Efficiency here is 100%. So that just means 1 is equal to AMA over 8. And AMA must also be 8. So let me actually erase this now. Okay, so now let's look into the other stuff we need to find. Okay? We need to find the ideal effort. Or the real effort as well, because actual mechanical advantage is the same as ideal mechanical advantage, right? So we need force in. Actual mechanical advantage is equal to force in, force out, because force out must be greater, right? Over force in, because you have a mechanical advantage, because the force exerted by the machine is greater than the force exerted by you. So force out here would be 94.6 kgs, right? 94.6 times gravity, the work done by gravity. So 9.8 meter per second squared. Over, so let's see, 94.6 times 9.8. That's in newtons, right? So we have a force here, divided by force in. And actual mechanical advantage is 8. So force in is equal to 94.6 times 9.8 divided by 8. So this should give me about 115.88 newtons. Or I'll just round up to 115.89. Yeah, I'll just round it to 115.89. Okay. Now what? So I have what I need, my force in, and now I need to know the work done by gravity, okay? Here, this is just the force of gravity. What's my work done by gravity? So work is just, if you remember, force times distance, right? My force here is 94.6, which is force of gravity. 94.6 times 9.8. So what's that? 927.08 times D is equal to work done by gravity. So how much did I move up here? Basically, what's the change in my height here? So that's going to be my distance, right? How much did I change in height? Or I could use mgh, but you understand how that would give you the same answer, right? This is mg. Distance is just how much it moves up. So in a way, it's height. So let's see, how much does it move up here? So the mass rises 4 meters, okay? If the mass rises 4 meters, which we can understand why it rises 4 meters, right? IMA is 8, and then AMA is also 8. So you could use, basically, you could use force out over force in, right? That's equal to 8. So that means distance in over distance out must be 8. And then if you find out your force in and your force out, you could probably find out this as well. But we're not going to look into that right now, okay? If we say that the mass rises 4 meters, okay, let's just say it rises 4 meters upwards, and then what's going to happen? 927.08 times 4 for distance times 4 is about 3708 joules. So you could use this, or you could use the same mgh, right? But either way, it's the same answer. So this is because gravity is acting in the negative direction, right? So that's where that comes from. Okay? And if you're confused on where I got the distance from, that would just be from the IMA would be equal to the AMA, right? And then you could set those equal together and find the distance. But if that confuses you, don't worry, you won't be asked a question like that. Just imagine the mass rises 4 meters, okay? Then you can see what happens. Alright, so that's it for today's video. And stay tuned for the practice problems regarding pulleys. So, because I'll find a way to make these even harder, okay? But that wraps up this unit, the unit of energy, conservation of energy, as well as pulleys and mechanical advantage, and IMA and AMA, okay? So stay tuned for more videos, but otherwise, that's it for now. Make sure to give me a like and subscribe so I can help others out, as well as keep helping you.